So good afternoon, everybody. Hopefully your internet is all working fine now after the maintenance to the Asia America Gateway. So today we're going to look at Magma evolution, and today is going to be a lot more calculations. There's no thin sections in this practical, it's just calculations. We will look at more thin sections next week, but for the moment, calculations. And so these, you can either, like the previous practical, you can write the answers on the handout itself and scan it, or on another in another document. Some of these might be easier to do in a spreadsheet. So if you want to use Google Docs or Excel or something to try and do the calculations, do that, and then upload that file to us for marking. So just make sure that however you do hand it in, you have your name, your section, your ID number clearly, and you make it clear which questions you're answering. So the first part of this is on Stokes' law. So this is the settling velocity, so how fast a crystal will settle or will float. It's not just for crystals. So as we'll talk about a bit in the lecture this afternoon, you also get this same equation for particles dropping out of an eruption cloud. So it's a very useful equation. So this is just here to remind you what all the terms are. So v is the velocity, what you usually want to know, how fast will the crystal that you're looking at settle. And remember that v is defined to be going downwards. So if you get a negative value, it's actually a crystal going the opposite way. So it's not going down anymore, it will be going up. G, gravity, you can just assume it's the same as at the surface because we're only looking very, very, very top bit of the Earth when we're doing these calculations. If you were trying to work this out for something in the outer core, the liquid outer core, for example, you wouldn't be able to use this value. But for our purposes, 9.81, 10 even is probably close enough. It's all an order of magnitude here. R is the radius of whatever particle you're looking at. You have rho here. It's not a P, it's actually a Greek letter rho. And this is the density of the particle, the RS, or rho solid, and then also of the liquid. And eta, this Greek letter eta, funny little n, is the viscosity, or how easy it is to flow. So a high viscosity, it means that it's very sticky, it doesn't flow very easily. So the questions here will ask you how to calculate the settling velocity. So this should be fairly simple. You have one as for an olivine crystal in a basaltic mount. So let's okay. So I've been told that you can't really see where I'm pointing, so I will start drawing. Okay, so what we're playing velocity of an olivine crystal. Let's use some different colors. Olivine crystal. Let's say you want to check olivine, so you want these values for this one, and you want it in a basaltic melt. That's in a basaltic melt. In this case, you want to look at basalt. You have all the values here, and you have your equation. The equation here. So you should just be able to put these numbers into a calculator and get the answer. Calculator. Doing that now. Apologies for the delay, WebEx is rather slow. So hopefully you can see the calculator. Then off position. So you just plug the numbers in. So you have 2. So you actually make sure that you, when you're dividing, you make sure you divide by the correct number, and show you're working. So don't just give a number, because if you just give a number and it's wrong, you will get 0 marks. If you show you're working, and I can see, oh yeah, you understood what you're doing, but you maybe forgot the 2, or you forgot to square it, or there's just you just slipped and pressed the wrong number on the calculator, you'll still get some marks if you show you're working. If you don't show you're working, you just get a 0 if it's wrong. So show you're working, remember the units, because if you just get a number and it's 10, that doesn't tell me 10 what? Is that 10 meters per second, 10 kilometers an hour? I mean, it's very different numbers. So make sure you include your units. You'll lose marks if you don't include your units. So for this, just so yeah. So the bottom here is 9 times eta, and here this 10 to the 2 is 10 raised to the power 2. So that's 10 times 10, it's squared. Here it's 10 to the 6, so that's 10. So for a rhyolite, eta is 10 to the 6, so that would be 10 times 10 times 10 times 10 times 10 times 10, so 10 6 times. And so on my calculator here, I have a button 10 to the x. That would be 10 to the 10. So, so for 10 to the 6, for example, I could go 6, 10 to the 6, and then it's 1 followed by 6 zeros. So the basalt, it's 9 times 10 to the 2, or times 100. So the bottom, you need to divide by 900. The top, just plug in the numbers. And remember, you do what's in the brackets first. And if you have a calculator that you can put the brackets in, then you can use that. Work it out bit by bit. So it's the difference in the densities that matter. So row S is, for the first question for olivine, so it'd be 3,300. minus in your basalt, which would be 2,900. So the difference is 400 kilograms per meter cubed. Multiply all the numbers together. Just to make sure you square your R. That will be 2 millimeters. And here's where it's important to get your units right. I suggest you always use SI units. So that is meters, it's kilograms, it's joules, it's pascals. And that way, whatever you get out is going to be in SI units. So if you put all of these on the right-hand side of the equation, it will be velocity, it will be meters per second. I mean, you can, if you want it in millimeters per second, you could change all your other units, but you'd have to change your viscosity, you'd have to change your densities. So the easiest one, use SI, make sure that this is meters. So 2 millimeters, 0.002 meters, and then we can square that. So that's squared. Multiply it by gravity, 1, multiplied by 2, multiplied by the difference in density, which we had was 400. So the top, get that number, and then you divide it by what we had at the bottom, which was 900. And so here you get a number, and think about the precision. All these numbers here in this table are round numbers. I mean, the most significant figures you have here are 2. So significant figures are any number other than a leading or trailing 0. So annotate again. So here you have the 2,900. That's your significant figures. These 0, 0 here, that are the trailing zeros. Given that we rounded all these numbers, your final answer, you're not going to know that to perhaps this many numbers. To this many numbers, quite a lot of numbers. You probably only know it to 2 significant figures. You just want the first 2, the 3 and the 4. And so you would round it up because 8 here, this 8 is bigger than, it's more than halfway to 5. So you would write this as 3, 5, with all the zeros. 0. With all those zeros there. And if you want to convert it to powers of 10, you can. So there's 1, 2, 3, 4, 5 leading zeros in this case. So this would be before you get your first digit. So it would be 3.5 to the minus 5. But you don't need to write it like this. If you just write it out as 0.0000035, that would be fine. Remember your units. Because we used SI units for everything, we can say that it's meters per second. Okay, so that should be fairly straightforward. Then need to do the same thing for a feldspar crystal in a rhyolitic melt and a feldspar crystal in a basaltic melt. So again, here you just use the same values that are in this first table here, just change instead of olivine and basalt, feldspar in rhyolite, and then feldspar in basalt. You do the same thing. And so, yeah, just work through your answers, put down your answers. A couple of questions here to make you think about what these answers actually mean. Go back to the lectures if you don't understand what these answers mean. We did go over them a bit in that. If you don't understand, come and ask. So the next bit of the practical, so the rest is actually looking at partial melting and fractional crystallization, and I spotted a typo here. It should be partition coefficients, not patrician coefficients. Anyway, it's all using partition coefficients that we went over in the lecture. So this first bit is just explaining again what we went over in the lecture, so you can read it if you don't remember. Remember that the partition coefficient is the concentration of an element in mineral divided by the concentration in the liquid. And so it again. So here, notice that there's a bar on top of this D. This is the bulk partition coefficient, or the average. So if you have a rock that has multiple minerals in, so here we have an example of a garnet peridotite. So it has olivine, 60% olivine. It's mostly olivine. It has orthoperoxine, some clinoperoxine, and a bit of garnet. So it doesn't actually matter what these minerals are in particular, but you should have seen most of these minerals. I don't think you've seen garnet yet, but this is what this rock is made of. And so what we do for each of these minerals to work out what the bulk partition coefficient is we take the W, or this is the weight we give it. This is the proportion of the mineral in the total rock, and we multiply it by the partition coefficient of that mineral. So in this hypothetical example here, we take the olivine, and so these values here, the 0.6, this 0.6 here, comes from the 60% up here. Remember, this should be a fraction between 0 and 1. Otherwise, your bulk partition coefficient would be 100 times the individual partition coefficient, which is not what you want. So this first bit should be between 0 and 1, so 60% is equal to 0.6. Multiplied by the partition coefficient, which for olivine is 0.01. This is in a, you get this from a table down there somewhere. We'll get down to it. It's lower in the, it's further on in the practical. So you do the same for the orthoperoxine here. It's 0.25 because it's 25%. You add these together. You then add the same for your chronoproxene and for your garnet. And for your garnet. And then you get an answer when you add all these together. Again, show you're working. Now you may be thinking, I'm always saying you should show your units. So what unit should this be? I haven't shown any units here. And that's because actually that for a partition coefficient, there are no units. So if you look at the equation, it's concentration in the mineral divided by the concentration in the liquid. If your concentration in the mineral is in parts per million, and your concentration in the liquid is also in parts per million, you have parts per million divided by parts per million, and so it cancels out. The ratios usually don't have any unit, unless the top and the bottom has different units. So if it's a ratio of, say, speed over time, then you have, or distance over time. So speed, for example, is a ratio of distance over time. Then you have meters divided by seconds. In this case, it will be parts per million divided by parts per million, and your unit disappears. So in this case, you can't put in any unit. But when you're then calculating further on, you'll then be asked to calculate concentrations. You do need to give units then, because there's a difference between like 10 parts per million and 10%, or 10, yeah. So there's a difference between that. So here are your equations for batch melting and Rayleigh fractionation. These are the equations that we went over in the lecture, but they're here again, so you don't need to keep going back to the lecture to find them. And here is just a table of partition coefficients. So notice, so you have your different minerals here. So they have different partition coefficients. You also have different elements. You have cerium, terbium, nickel. And don't worry if you don't actually remember what CE stands for or YB. A lot of geochemists don't actually know what they stand for. In my head, these often come up as like erbium, barium. I don't actually remember them all. So, but you just need to know that this is what the partition coefficient is, and then you can say, okay, this is how much CE there is. But this is cerium, this is ytterbium, this is nickel. If you want to, and notice that olivine, that nickel is really compatible in olivine. So nickel likes to go into olivine. It also quite likes to go into orthoperoxene, although not quite as much. But then things like plagioclase and tridymite, it's really incompatible. So if you have a rock made up of mostly plagioclase or mostly tridymite, then the nickel will stay in the, will tend to stay in the melt. If you have a rock made up mostly of olivine and clinoproxene, the nickel will go into the crystals. So the partition coefficients vary depending on the mineral, but each mineral will have a different partition coefficient for different elements. So if we look at olivine again, for cerium here, there's a really low partition coefficient compared with nickel, it's really high. So the questions here will ask you, so first you need to calculate the bulk partition coefficient. If you want to calculate how much of an element will go into the melt, how much will go into the crystals, first you need to calculate your bulk partition coefficient. So these questions, so it asks you for the 3 different elements, and you have your rock here with 5% tridymite, 55% clinoproxene, 40% plagioclase. So you can use the formula for the bulk partition coefficients first. So this one, equation 3 here, to calculate the partition coefficients. And this you can either do with a calculator by hand, or you could do it in a spreadsheet in Excel. So for this, let's say question 2.1. We want cerium, erbium, nickel, and you can calculate your partition coefficient here. So what would be the best thing in the spreadsheet? So you can maybe put in. Actually, I should have had one that I made earlier. So here's one I made. A tip: if you have Excel and you paste it and it doesn't go nicely, you can use this. So in the 2016 version, it moves around in whichever version you have. And the data is text to columns. And you can choose, so delimited means that each column is separated by, in this case, a space. You tick, if I finish, there, you split them up nice. So we know for cerium, so this would be equal to, so we want 5% tridymite, so 0.05 multiplied by the partition coefficient tridymite, plus, and I'm putting this in brackets to make sure it does the multiplication first, then the addition. Then we put in brackets the next one, so it's 55%, so 0.55 multiplied by, which is this one, clinoproxene, 0.1, plus 40% plagioclase, so 0.4 multiplied by plagioclase partition coefficient, and we calculate it, it's 0.9505. And again, remember that most of these you see here is they're almost all just to one significant figure. The numbers here, the percentages, are 1 or 2 significant figures. So giving it to that much precision is not really really useful. The numbers we put in aren't that precise, so we're not going to get that precise a number out. So I'm just going to reduce it, so show 2 significant figures in this case, because there are some numbers that are 2 significant figures. And actually I can, in this case, just drag it across, and it will, Excel will automatically move the cells. So because I've moved one cell to the right here, it's moved all the input cells one to the right. So it's giving me the partition coefficients for each of the other elements. One thing you should always do when you calculate something numerically, you should do a quick sanity check. Does this number seem right? So here, for example, cerium, does a partition coefficient of 0.095 seem right? So when you look at what the rock is, it's made up, here it's made up of tridymite, of plagioclase, clinoproxene. Most the clinoproxene and the plagioclase is about 0.01, 0.1, sorry. The tridymite is much lower. But it's mostly clinoproxene and plagioclase, so we would expect our partition coefficient to be close to the partition coefficient for clinoproxene and plagioclase. A little bit lower than that because the tridymite will bring it down. And when we look, that's what we get. So it seems about right. It's just a little bit lower than the partition coefficient for clinoproxene and plagioclase. If this had come up as 10 or 0.0001, we would think, hang on a minute, that doesn't seem right because it doesn't match the partition coefficients we have here. It's a long, very different. So maybe I've done something wrong. And then you go back and check. So we always, whenever we do any calculation, just that sanity check. What sort of size number do you expect it to be? Do you expect it to be 1,000,000? Do you expect it to be -1,000,000, 10? And if it's very different from that, you go back and check it. If it's close to what you expect, then you can be fairly sure that you haven't at least made an obvious error. And it's easy to make an error. You divide instead of multiply, or you forget to do the whole formula, or you use percent instead of the. I mean, if I had forgotten to change this to proportions, I'm going to say 5 times G9, 55 for the 55%, clinoproxene for the is a so I'd look at that 9.5. That doesn't seem right to me, and so I go back and then look at what I did and say, oh yeah, it should be proportions, not percentages, and then you change it. And this is, I mean, that kind of thing, doing proportions instead of percentages, it might seem like a silly mistake to make, but I do it all the time, especially given that people often use both for mineral compositions. Sometimes when you're looking at plagioclase, people will give percentages for the amount of calcium. Sometimes it will be as a proportion, and so it's easy to get those sort of things mixed up. But if you have in your head what you think the answer should be, then it's easier to not make those mistakes. So then for the next question, it says this rock contains 5% cerium, 2% terbium, and 100% nickel. So there's a rock with these, so these values here. So you want to calculate the abundance of these elements in the melt after 1 and 5% melting. I am sorry, I have not written this. Yes, I did not. So I should have specified which equation to use. So for all of these, if it doesn't give you an answer, I will correct this and put the new the corrected version up on the Moodle after this. After this introduction, but if you have the old one, this should that. Yeah, so I'll correct this to make sure the one that's out there. But if you have the old one, remember it's batch marking. And if you use Rayleigh fraction here in this thing, but you said that's what you were using, then I would have to give you the marks because it would be a correct answer to the question. So this is where it's important to be clear in your working. If you said, I'm assuming Rayleigh melting, and you've got all the calculations correct, then I would have to give you the marks for being correct. But if you just put down the numbers and I had no idea where you got the numbers from, I might mark you as wrong because the numbers you get wouldn't match the numbers I was expecting. So always show your work. So we're going to assume here batch melting. So we're using this rock, so it has these partition coefficients. And so we can set up a table here with we need the 3 elements. And you can do all this by hand with a calculator and work it out, but it is a bit easier if you have a spreadsheet to do it in. And you can get Google Sheets for free on the internet or on your phone, or I think there's Excel has a free version as well. So here we'll do the melt fraction. And the equation you're going to be using. The batch melting here. It's the same for the Rayleigh fractionation. So remember that you have this F, and this F is the melt fraction. So this again is a 0 to 1, not as a percent. So the question gives you a percent of melting. You need to turn that to a fraction. And again, this is why it's important to show your working. If you calculated it and you used a percentage instead, then you'll lose a mark for using the wrong, not converting it, but you get all the rest of the marks for the question. Because I can see, oh yeah, you did use the right equation, you put the numbers incorrectly, you calculated it correctly, you just forgot a little bit. So the melt fraction will be 0.01. So if we go back to our equation here, we can enter it. So let's move these down. And so 0. So this is how much there is to begin with, because we need that. The C0 here is the initial before any meltings happened. So we can put those in here. 5, 2 terbium, and 100 nickel. And if you're using Excel or something, if I put 5 ppm, for example, and then tried to calculate something with that, maybe that times 10, going to come up with an error. So you can't actually put your units in, because it will think it's text, not. If you could put it at the end like that, you could put it here to 0 ppm. There's a couple of different ways you can put it in. Just make sure it's clear that you have the unit somewhere there. And this, I mean, might seem a bit artificial here in terms of just doing a worksheet, but it is actually important when you share your data with other people. I have a whole lot of geochemical data, and it's important that I remember what units everything's in. It's important if I share it with other people that they know what units it's in. Otherwise, so it's important for you, if you don't write it down, you can forget. You can come back to your data in 5-10 years' time, and you can't remember. It might seem obvious at the time. And if you give it to someone else, they don't know at all what units you use. So make sure you do record your units somewhere on these tables. So now we have C0. We know what melt fractions we're after. We can actually work out using the equation. So CL over C0. So what the question's actually asking for is the concentration in the liquid, the melt. So it's this. And what the equation here gives you is this, CL over C0. What you have to do is you have to take your C0 and move it up that way. So you're multiplying both the left and the right-hand side by C0. So you end up with so you cancel it out there. That's C0. You just rearrange the equation, then it's in terms of CL. So the equation would be equal to this divided by, and I'm going to put all this stuff on the bottom in brackets, so it's all, you calculate all of the bottom before you divide it. So F, the melt fraction, 1 minus F multiplied by, and again, make sure you use the right number of brackets. It multiplies before it adds, and you want to multiply it by your D, which you calculated in the previous question. Close the bracket, then you enter it. Again, make sure that you give a sensible amount of precision. No point giving it to that many decimal places because we don't know any of the other numbers to that many decimal places. Now, I'd be careful in rounding any of your numbers early in the equation, early in your calculations, because that can bring in errors. So if I'd rounded this and just called it 0.95, you would end up with a slightly different answer here. And if you do round it as you're going, I'll check and make sure as long as your numbers are consistent, you'll get the marks. But it's better to only round at the end of all your calculations. Using this function here to increase or decrease the number of decimal places displayed in your spreadsheet doesn't actually round the number. Excel still stores the entire number here, just shows a different amount of precision. Another useful tip for Excel, if you have a value that you don't want to change, so if I drag this across now, it's not going to work, because if we look at this, it's moved from the melt fraction to there. It's moved this one to the right place, so the partition coefficient up there, but this one, it's moved to the right. But you don't want these to change ever. So that's in our formula here. So for your C0, it's always going to be in row 14. So we can put a $sign before the 14. Then if we move it down, it's not going to change. If we move it across from A to B, this B will change. But if we change it, go down from row, because it's currently in row 15, if we go down to row 16, this 14 will not change. Same for the melt fraction. We might want to go, we never want to change the column. We put the dollar before the A, but we don't put a dollar before the 15. If I put a dollar before the A and the 15, it stays on A15 forever, no matter how much you move it. But we might want to go down and change the melt fraction down, but as we go right, it always wants to be in column A. So we do the same here. And actually for the partition coefficient, we don't want to change the row, so we don't put a $sign before the B. But we do want to change the column, because as we go from column B, working out cerium, to column C, working out ytterbium, we want that to change. We put in those $signs, we then drag it across, and then we just check that it's all the correct ones. Yes, you see now it's gone across to the partition coefficients changed from B4 to C4, but the melt fraction hasn't changed from A15 to B15, it stayed in A. So we can drag this across nickel, and then we can drag the whole row down, and this then should and we can copy that one. So you should see how the concentration changes. So you have here so you have cerium and ytterbium are both incompatible elements in this rock, and so you see as you start to melt, they get enriched in the melt. All the cerium goes into the melt. As you increase the melt fraction, it's the amount of cerium in the melt, the concentration of cerium in the melt decreases. It's not because the amount of cerium has decreased, because you now have more melt. You melted more of your rock. There probably is a bit more in terms of the total number of atoms of cerium, but it's now more dilute. Same with ytterbium. So this, to me, it looks a bit strange. Should it be the same? Maybe it has actually changed a bit, if you see. So maybe for this, you want to increase the number of decimal places just to see the change. So maybe 3 decimal places is worth showing here. And you can see its nickel is slightly compatible because it's slightly above 1, but it's not very compatible. So actually we wouldn't expect the amount to change so much. But because it's close to 1, you would expect there to be a similar amount of nickel in the solid, in the crystals, and in the melt. And that's what we actually find. And it doesn't change so much as you increase the melt fraction. And if you're really keen, you can then just you can calculate more. It's very quick. I could go 0.1. You can write this down, and you'll see how it changes. If you want to play around with it and graph it and see how it changes, you don't need to do that, but if you want to. So that's how you do question 2.2. Question 2.3, so you now have a different rock, the garnet peridotite, with 60% olivine, 25% orthoprotein, 10% clinoprotein, 5% garnet. And here you have the concentrations in the original rock. So here, it's after 1% partial melting. So in this question, you have to first calculate your bulk partition coefficients by using this, and then you calculate the concentration in the melt after 1% melting. So you just have to do the same thing, but you have to then do the two parts of it. And then you do the same, but this is after 10% melting. So you just then add an extra line to your spreadsheet and do 10% melting. And then here, so I want to look at the concentrations. In the two melts. So this is in the what was I trying to ask here? So here you want to compare the melt you've just worked out here, so the 1% partial melting, with the melt from this question, from question 2.3, and just compare the two concentrations. Where do you think this would be useful? How would you be able to use these kind of is that what I was asking? No, so have a look between the 1% partial melting of this rock, this garnet peridotite, and the 10% melting of this garnet peridotite. And see how do the concentrations change as you go from 1% melting to 10% melting, a bit like we just discussed here for the 1 and the 5% melt of this rock. And so what conclusions can you draw? What can you say about the behavior of the different elements? So here, question 2.6, again, different rock. So you have, so here now we're moving on to fractional crystallization. So here you have a melt with these concentrations. Then you crystallize 10% as olivine. So here your F, your melt fraction is 0.9. Please remember the melt fraction, it's the fraction of melt. Although this time you're going backwards, you're going from 100% melt or melt fraction of 1 to a 90% melt, to a melt fraction of 0.9. F is still the amount of melt, not this 10% crystal, so it's 0.9. So what happens to this melt when you crystallize 10% olivine? So in this case, you don't actually have to work out the bulk partition coefficient. So this calculation here that we did, you don't need to bother with because it's just olivine. You can just read these values straight off this table. And you would do, because it's batch fractional crystallization, you do exactly the same calculation that you do here, but in reverse. And if you're wondering what your C0 is, that is these contents here. So remember, if you remember when we were doing partial melting, this C0 was the amount of that mineral in the solid. Here we're doing it in the melt, but the reason that works is because if you have 100% melt or 100% solid, you have to have the same concentration, because we're assuming in these calculations that there's no addition of material, there's no removal of material. So what you start with is what you end with. So if you have 5 ppm in solid, you melt all solid, you have in the liquid. Yeah, so again, you just do the same sort of calculation you did here using melt fraction. So now do the same thing, the same as this, but you want to calculate it using Rayleigh fractional crystallization. So here, just show you quickly what we would do. Again, we need to know what, so this would be melt fraction of 1 this time. And so it has, so we read off these numbers because it's the same melt before. So we're saying 20 ppm cerium, 2 ppm terbium, 200 ppm nickel. And now we're on 0.9 as our melt fraction. And now we can calculate it. Remember, it's 10% olivine, so it's just olivine. The solid is 100% olivine. Yes, so don't get confused and try to calculate a bulk partition coefficient assuming 10% olivine, because the proportions which you put into your bulk partition coefficient are the proportions of that mineral the amount of that mineral as a proportion of the entire solid. In this case, the entire solid is 100% olivine because there is no other minerals crystallizing. So we can just take the partition coefficients olivine here, and so if we go back to our calculation for so here we have this calculation here, and remember the C0 at the bottom here, we want to move that over to the right because we want the concentration in the liquid alone, not the whole ratio, just that. We multiply both sides by C0, so we would get, this would be equal to C0 multiplied by F, this one. Then we don't want the row to change for our C0, don't want the column to change for our melt fraction. We put the dollar signs in the right place. And this is, so we raise our melt fraction to the power, so we use the roof, on my keyboard it's over the 6. If you're doing it on a calculator, there might be a difference. When you have to work out, every calculator is different. So here I have x to the y, so I type in, you'd have to work out which way it is. So if let's just check, I do that, y2, does that give me 200? That gives me 100, yes. So if I go to 10, that gives me, so if I do it that way around, it gives me 2 times 2 times 2 times 2, 10 times. If I do it 10, 2. So just check on your calculator which way round you have to do it. If you're doing it by hand, you can calculate the bit in the bracket here first and then put it into your calculator, so that the d minus 1. If you're doing it in Excel, it's much easier. You can just put the raised to the power thing symbol and then put in brackets D. So your D in this case would just be olivine. Again, we don't want the row to change, so we'll put a $sign before the 4, and it's minus 1. And so just do a little sanity check. So cerium is incompatible in olivine, so we would expect it to increase slightly in the remaining melt because you're taking away the olivine and you're leaving just and the cerium is staying in your melt. If you have slightly less melt, the same amount of cerium more or less, because very little will go into the olivine, so you're increasing the concentration. So if we drag this across, ytterbium would be the same. Maybe we'll actually make the 3rd decimal place. You see it's increasing slightly. Nickel, highly compatible. So all the nickel is going into the olivine. You're taking the olivine away, and so the amount of olivine, the amount of nickel has decreased quite significantly. So yeah, so 2.7, calculate these numbers, and then yeah, and have a look and look at how these numbers here vary compared to the numbers you calculate in 2.6. Here you're assuming batch fractional crystallization. Here you're assuming Rayleigh fractional crystallization. Would you expect them to be the same? Compare them and see how they look. So here, question 2.8, you have a basaltic melt. The fact it's basalt doesn't really matter. This is the concentration of the 3 elements you're interested in. This time, you're not just crystallizing olivine, you're also crystallizing clinoprotein and plagioclase, and this is the ratio between the, so you have 10% olivine, 40% clinoprotein, 50% plagioclase. So that's all that means. 10 ol, 40 CPX, 50 plag. To this case, in this case, you have to work out the bulk partition coefficients again of this solid. And then you can calculate your Rayleigh fractional crystallization. So you just do this equation here. But here we just could plug in the number straight from olivine. Remember question 2.2, we had to first calculate the bulk partition coefficients. You could do that here if instead of olivine, you wanted that, you can plug that number into your as your partition coefficient here, and it works just the same. So, but here, remember, you need to first calculate your bulk partition. The same with this. So what you're going to calculate for these 2 questions. So you start off with a liquid, and it's crystallizing olivine, chronoproxene, and plagioclase. And 50% of your melt is removed as those three minerals. Then when you get to this point, what happens is the olivine stops crystallizing. This kind of approximates fractional crystallization in the way that magmas evolve. So at some point, your magma will get so evolved that olivine doesn't want to crystallize anymore. And so this time, then after this point, you just have chronoproxene and plagioclase crystallizing with 20% CPX or chronoproxene, 80% plagioclase. So now you have to calculate a different bulk partition coefficient. So that you're taking the same melt, it's removing some crystals, then you're crystallizing different from it. And this time, 75%, we're going to assume that 75% of this new melt crystallizes. And you want to calculate the concentrations of the three minimum. So in this case, you take this as a brand new melt. You start from scratch again. You assume that, in question 2.8, you get an answer to question 2.8. You take that melt, assume that's 100% melt again, so a melt fraction of 1, and then you calculate everything from scratch, but with these different partition coefficients, because you have different minerals, and then you calculate 75% crystallization of the 50% melt before. So you start with 100% again, and then crystallize another 75%. Okay, and so that's the practical. I recommend that you do try and do it in a spreadsheet. There are apps for your phone to do this. I know I have Google Sheets works really well on Android phones. I think there's a Google Sheets for iPhone as well, so you can use that. If you have a computer, it might be slightly easier to type in your phone, but you can do it on your phone. I will accept the answers in Google Sheets. Either download the file and send it to me. I mean, preferably I prefer you do it that way. If you can't work out how to do that, you should be able to send me a link to it in the cloud, and I can mark it that way. But if you want to do it by hand on paper with paper and pen and a calculator, that's fine too. Scan it in and send me the answers. So, any questions? And you probably need some time to go over it and look at it. But if you have any questions as you go through the practical, you can send me a message on Moodle and post it in the Facebook group. I mean, that's actually probably a good place to do it, because that way, when I answer you, everybody can see the answer at the same time, and you're probably not the only person wanting the answer. So use the Facebook group for that. You can post there. You can send me a message on Moodle too. I'll try and answer you as quickly as possible there, or in the office hours. So the office hours aren't just they're not restricted to any one topic. If you have a question about the practical, ask there. If you have a question about last week's practical, or about the lecture, or just any questions about the course in general, you can ask it in any of the office hours. Okay, so hopefully that will help you go through it. Yeah, you'll have 2 weeks again to actually finish this, to hand it in. But try to do it within a week so that you can so you don't get too you don't have too much to do at once because you will have another practical next week, another lab. Okay, so if there are no questions, I will stop recording. Okay, I'll stop recording.